do not understand the pattern. Somebody figure out the pattern this semester. It's driving me crazy. It's been like 2 years. I can't figure it out. Sometimes I open that recorder and I can hit record with the pen, and other times I can't.
If you accidentally slide the pen a little bit, it doesn't count.
I don't think so. I've tried it a million times. Sometimes I have to go back to the computer and hit it with the mouse. Can't figure out. Maybe I touched something on the board that allows pen recognition. I don't know. Okay, so anything lingering from homework or quizzes or anything before we start doing formal review for the exam that's on Thursday? So the exam, if you look up here in our review section, here's an overview. You can bring a calculator that's not a graphing calculator and that doesn't have an integral button. So you can't use those cool TI-36s that have the integral button. Is that one of those cool TI-36s that has the integral? So we have those calculators up there that you can use. Those are Casios. If you don't like using a calculator you've never used before, you could get one of those TI-30s, I think they are. Little blue ones or one of those. Yeah, just no integral button. Okay, so we've got a whole bunch of review exercises here. We aren't going to be able to go through all of them. They all do have a video solution, though, so any one that we don't get to, you can go and watch the video and see a solution to it. These problems are the ones that are also in my math lab. There's a homework, or I think I have it set as a homework, that you can work those problems. So they're same problems. They're in both places. Is there one in particular you want to see, or should we just start to go through in order? And
number 16.
16? I don't see 16. 16 in what section?
The practice for exam 1.
Okay, so what was the topic? Was it a work?
It's for find the surface area.
Oh, surface area. Yeah, okay, so we've got 2 surface area ones. Surface area is a good one. Let's go through that. Does it matter which one of these?
Oh, it's this one.
That one? Okay. So let's go ahead and do that. So surface area. One rule of thumb that I've mentioned a couple times that's not obvious, but if you can use dx when you're rotating around x and dy when you're rotating around y, that will make it a little bit easier. If you're rotating around x and you want to use a dy, or around y and want to use a dx, you can actually do it, but it's a little harder. So if you can just remember that going around y, use a dy for surface area. That's going to make your life a little bit easier, a little less thinking involved. So this one says, let's rotate around the y-axis. But the glitch here is that they are presenting the function as a y value. So it's measuring vertical distance and not horizontal distance. So if we're going to go around y, my recommendation is to convert this function over to an x value. So if we cube both sides of the equation, we'll have y cubed equals 3x. And then if we isolate x and move it to the left side, because that's where we usually put our dependent variable on the left, we will have that x is equal to 1/3 y cubed. Okay. And we need a derivative. Anytime we have arc length or surface area, we need to take the function and find its derivative and then square it and add 1. So we've got that whole arc length process, whether it's arc length or a surface area, we have to do this process. So let's go ahead and take the derivative here. The 3 comes down, so this is the power rule for derivatives. It cancels with the 1/3 in front. We subtract 1 from the exponent. So there's the derivative, and in this case, it's no big deal. It's not going to save us a lot of space, but we do need to have the derivative squared at some point when we put it into that square root, that ds conversion. So that's going to be our derivative squared. So what we're thinking of here is that let's think about a horizontal. It's not really an element, like it's not a rectangle in this case because we're not creating a solid object. We're just rotating this single point. So I'm drawing it dashed. It still sort of has the same implication as a horizontal rectangle. It means that we're integrating with respect to y. It's just that, you know, it's not really a rectangle because we're rotating just a point around creating a circumference. And this is at a random y. So that's what we're thinking of. And when that point rotates around, it's creating a circumference, a 2 pi r. So our formula for surface area is the integral of 2 pi r ds. We don't know anything about s. We don't have a tape measure that's bent on the curve measuring a arc length this way, so we can't use the ds. We have to convert it to either dx or dy. We're choosing to change it to a dy. So our generic formula, our choice here, is that we could change this to a dy or a dx. We're choosing to write it as a dy. And so inside the square root is 1 plus the derivative squared. In this case, it's x prime squared. If we chose to go vertical with a dx, then it would be 1 plus y prime squared. So there's our setup. So if we have a dy, we need y limits of integration. They've given us an x interval. So we are going to need to convert that. So we're going to have our 2 pi r ds, but we're going to have to find y limits there. And from the picture, it's pretty obvious that the y limits are 0 and 2. To get those, though, if it wasn't so obvious, if you didn't have a picture that made it obvious, we would simply take this x coordinate of 0, plug it in. Let's plug it in over here is easier. Plug 0 in right there, and we would get y is 0. If we take 8/3, plug it in here. 3 times 8/3 is 8. The third root of 8 is 2. So we would get our y limits. So 0 to 2 for those y limits. And now let's replace this r, that r, with what it's equal to. So r is the radius, so that's right there. And what is the radius? What is measuring this distance from the y-axis over to that point? The function. That's what the function is measuring. Right, this function is now measuring horizontal distance from the y-axis. When we isolate x in the function, it's measuring from the y-axis over to the curve. That's what r is representing. It's representing the distance from the y-axis, the axis of rotation, all the way over to the curve. That's what the radius is asking. Right? What is that distance? And we can say, oh, well, it's 1/3 times y cubed. So there's the radius. And then we have the whole ds thing. This piece here, remember, is just ds, arc length. So we have to replace that. We have the square root of 1 plus, and we found that the derivative squared is y to the 4th power. So there is our complete setup. Let's go ahead and pull the constants out to the front here. So we're going to have 2 pi divided by 3 all the way to the front. Integral 0 to 2, y cubed, square root, 1 plus y to the 4th, dy. How's that set up for everybody? Anything there? causing you grief. What will be our technique of integration here? U sub. We look inside the square root. We always go to the inside of whatever. Trig function, square root, exponential function. Inside would be the exponent. So that's going to be the u. When we take that derivative of a quartic, we'll get a cubic, and there's a cubic sitting out in front. So that's all copacetic. That should all work fine. So let's go ahead and do it. So we're going to let u be 1 plus y raised to the 4th power. We take the derivative of both sides here. We get that. When we look over at our integrand, we see a y cubed dy. So we could isolate y cubed dy here, writing y cubed dy as du divided by 4. So now we can do our substitution. Bless you.
Thank you.
We'll have 2 pi divided by 3 integral. Okay, so the square root part becomes square root of u. And then, that's not a u, square root of u. And then the y cubed dy becomes du divided by 4. And 4 is a constant in the denominator. It's simplest just to pull it out. We can put it all the way out in front. And then here we have a choice. We have a choice to convert over to limits of integration that are now u's, or we could put placeholder limits and then come back to the original y limits if we prefer. It does not matter. When we get to integration with trigonometric substitution, it's going to be easier to go back to the original limits. It's going to be less work. Here and in general, usually it's just, if this is simple to convert over, then go ahead and convert over if you want. If you want to just do it the same way every time and go back to x's, or y's in this case, totally fine. Here it's pretty easy to convert. So this is our conversion formula right there. This tells us if y is 0, plug in that y equals 0, we're going to get u equal to 1. If we plug in y equals 2 here, 2 to the 4th is 16, plus 1 is 17. So that would be pretty easy to convert to u's. So in this case, let's do it. Out in front, we're dividing by 4, which means multiplying by 1/4. So we're going to end up with pi divided by 6 when we cancel out a 2. And then we're going to integrate u to the half, so we're going to get u to the 3/2, adding 1 to 1/2. And dividing by 3/2 means multiplying by 2/3. So we'll end up with that. It looks like pi over 9. And then we're going to plug in 17 and get 17 to the 3/2 minus 1 to the 3/2. And 17 to the 3/2. There's no simplification in the sense that a square root would be there. 17 doesn't have a perfect square embedded in it, so we can't simplify it that way. A lot of times what you will see is a simplification just to get rid of the 3/2 power and write that as 17 square root of 17 minus 1. So that would be the, there. Did not like that. Try it again. So that would be our simplified answer. If you put it like this on the test with the 3/2 power, totally fine. Any part of that you have a question on?
Will you just scroll up to where you got the limits again for y?
Yes. So from this equation here, if you plug in x equals 0, 3 times 0 is 0, 0 to the 1/3 is 0, so that y coordinate. And if we plug in 8/3, the 3's would cancel, and then 8 to the 1/3 is the cubed root of 8, which is positive 2.
Okay, thank you.
Make sense?
Yeah.
All right, well, any other one you definitely want to see? Is there anyone that is jumping out at you as a definite?
Can we do some more applications?
Absolutely. So do you want to do work or force? Work. So let's go with, let's do the hardest one. Let's do the trough. We'll do the hard one. So we've got this trough. It tells us that the trough has a face that's got a trapezoidal face. The big base is 7, which is at the top. The little base is 3.5, which is at the bottom. So we've got that trapezoidal face. Let's draw it over here, just because it's going to be easier if we do that. So we've got that trapezoidal face with 7 up there, and I'm going to write it as 7/2 down here. So 7/2 is the small base. Cross. Not sure why. Let's put it right in the middle. Okay, so we have that. And we're going to draw a representative cross-section. So a cross-section is going to be a rectangle of water. So that representative cross-section is going to look something like this, all the way around, all the way down. So it's a big rectangle of water. It's corresponding on the face to a horizontal element that goes all the way across that we'll refer to as W. W is the distance all the way across the face. And our guiding principle is that the integral of area, I was going to say the integral of area is volume. Yes, that's true, but that's not what we're doing here. We're integrating in order to find how much work is done. So our guiding principle here is that we look at this cross section and we have to convert it over into our acronym, to our ADD acronym. And that cross section is going to represent area in our acronym. So let's get that on the board so we can start filling in blanks. So anytime we have work, this is our acronym, ADD volume. And that cross-sectional area is a part of the volume piece. And so we find the area of our cross-section, and if we multiply that by dy, we've turned the cross-sectional area into a slice. A slice has volume, a cross-section just has area. So when we multiply that area by dy, that's going to fill in the VOL, the volume. Okay. Now, in terms of the basic constants that we know for sure, we know that acceleration due to gravity is 9.8. We're told that this is water. Water has a density of 1,000 kg per meter cubed. And then the second D, distance or depth. Think of it either way. Distance from the top or distance that the water has to travel or how deep it is. Doesn't matter. Either one of those works. So how deep would that be if this is the general horizontal rectangle at y? How deep or what distance does that have to travel to get out if we're pumping it right out of the top?
7 minus 5? 7.
So the trough is 10 meters long. That's not how high it is. It's 7 meters high right there. So 7 minus y. So we just have to look to the right distance. This is 7 minus y. If all that's 7, then this part right there is 7 minus y. So that's our second D. 7 minus y. How about limits of integration? 0 to 7, because we're dealing with a face that's 7 meters tall. I don't like that they put a 7 in both those places. That 7 across the top has nothing to do with the limit of integration. That's going to have to do with the equation of this side. So that 7 right there is not what we're looking at. This 7 minus y is coming from there. Okay, and the limit, though, is that one right there. That's 7. Okay, now the hard part. The ADD part is usually the easier part. And just as a reminder, when we get into the force problems, ADD, if you were to look at the units on ADD, that's pressure. ADD is pressure. Okay? ADD is pressure. But we don't need to know that in this context. Now we have to find volume. Volume is area multiplied by dy. So it's the area of that red rectangle multiplied by dy. Hopefully it's clear that the rectangles all have different area because we've got that trapezoidal face. That W is changing depending on where that rectangle is. Right? So it's a function. In order for us to calculate the equation, we are going to need the equation of this line segment right there. And the easiest way to find the equation of a line segment that's not going through the origin, so this one is not going through the origin, we're imagining our coordinate system right there. A line through the origin, we could just use mx, y equals mx. But if it's not through the origin, easiest way is to use the point slope formula. So point slope formula. So we need to know 2 points on the line. And if we look right here, that point, certainly the y-coordinate is 0. What would the x-coordinate be if we put this coordinate system right in the middle of these bases? 0.25. So 7 over 2 divided by 2. So that's going to be 7/4. If we take 7 over 2 and divide it by 2, we multiply by 1/2. We're going to get 7 over 4. And then how about the point up here at the top? 7/2. We're going to take that longer base, divide it by 2, get 7/2, and then the height we're told is 7. So that's going to be the upper point. And I think we have space up here. When we use the point slope formula, we can use either point. I'm going to choose to use the point down here because the y-coordinate is 0, so y minus y1 is just y minus 0. Could use the other point just as easily. A little bit more work. You could do y minus 7, totally fine. Equals the slope. So the slope is the rise over the run from this point to that point. So the rise is 7. We're going to go up 7. So 7 divided by the run. So we're going to go up 7 and then over that distance. And what is that distance? So we're looking at that distance right there.
7/4.
So it's going to be 7/2 minus 7/4, which is 7/4. 7/2 minus 7/4 is 7/4. If you have to get common denominator, it's 14 over 4 minus 7 over 4, which is 7 over 4. So that will be our slope. Excuse me. Yeah, I got to write a 7 over 4 there. And that will be our slope once we simplify it. And then x minus the x-coordinate of the point we decided to use, so x minus 7/4. X minus 7/4. So that is the equation of that right-hand line. I'm going to come down here and rewrite it. So we have y minus 0, so we'll just write that as y, equals, we're going to simplify that slope. Dividing by 7/4 means multiplying by 4 over 7, so that all simplifies to just a 4. So 4 multiplied by x minus 7 over 4. So there is our right edge equation. What do we want to do with that right edge equation?
Make it in regard to y.
So we want to solve for x. We want to write it in terms of y, so we want to isolate the x. Because our goal here, to find the area, we need to know what W is. W times 10 will be the area of the cross-section. So W times 10, to find W, we need to know what the X value of the right edge is. So we're going to isolate X here. So let's go through that. We'll distribute this 4. So Y will be 4X minus 7. We're going to isolate the X, so we'll put the X on the left. Divide by 4. So that's X. So X measures from our vertical axis over to the right edge. W goes from the left edge to the right edge, though. It doesn't go from the axis, which is right in the middle, over. W is the whole thing, so what do we do to that X to get W?
Double it.
Double it. So W will be 2 times this. And if we distribute that 2, we're going to end up with 1/2 Y plus 7/2. That is the distance across the face at a height of Y. And you can check. It's a pretty easy one to check. If you're at a height of 0, you're 7/2 across the front, which matches the 3.5. Right? 7/2 is 3.5. And if you're at the top, where Y is 7, that should be the big base of the trapezoid. Plug in a 7, you get 7/2 plus 7/2, which is 14/2, which is 7, which is in fact the distance all the way across the top. So it all matches. So in here then, we are going to have 10 multiplied by W, which is 7/2 Y plus 7/2, and then multiply by dy to get volume. So all of this right here, that is volume. So volume is area multiplied by thickness.
I thought it was 1/2
1/2 Y plus 7/2. Oh, yeah, I don't know why I put 7/2. Thank you. 1/2 Y plus 7/2. There we go. Perfect. So that's the hard part, getting it set up. Is there a part of that you want to talk about? Finding, everyone understanding the concept that the volume is an elemental volume, so it's not the volume of the whole vessel, it's just the volume of a slice of water, horizontal slice.
When you found the slope and you first created the equation, when you had the x in parentheses with the minus 7/4, that's because it's translated 7/4 to the right, correct?
Correct.
Okay.
So when we're doing the inside there, we're picking our point 0. We're picking our point 0, 7/4. So it's y minus y equals x minus x. Yeah, and so that shift is moving over 7/4 to the right from the origin.
Okay.
Is that what you're asking?
Yeah.
Okay.
I was just making sure I understood that part, because when I first saw it, I'm like, what the?
Yeah. So it's from the whatever point we pick. And if we picked this point here, we would have x minus 7/2 and we would have y minus 7, and it would come out the same.
Just for how the problem is worded, like it asks how much work is required to pump the water out of the top of the trough.
Mm-hmm.
Is that just like the whole thing, or like
So the idea
the
is,
limits are 0 to 7?
so the limits are 0 to 7 because the water is we're imagining a drain right there. And so we're pumping out layers of water from 0 to 7, and we're just pumping them straight out.
So it's not the top of the water being drained, it's the water being drained out of the top.
It's the water's being drained out of the top.
Okay.
Yes, yeah. So there's a little pump up there at the top, and you open the valve or whatever, and the water's all going to come out the top, and it's the pump is down at the bottom, you know, like a fish tank.
Yeah.
It's just going to pump it all out.
All right.
All right, so now the math part, or the not really, the computation part. Let's see. One thing that we could do is factor out all the constants. So I'm going to pull them out in a couple of pairs. So 9,800 is that first constant right there. Over here, we could factor out a 1/2 and get rid of the fraction in there. That will make our life a little easier. So we're going to factor out the 10 with a 2 in the denominator, which will translate to a 5. All right, 10 divided by 2 is 5. So if we pull that out, then this is what we'll be left with inside the integral. We'll have the 7 minus y, and then this will be y plus 7 dy. So factoring out the 10 and the division by 2. And 10 divided by 2 is the 5. Okay, so let's multiply this out. That's 5 times 0, 5 times 0, 5 times 8 is 40. Carry the 4, so we have 45 plus 4, so it looks like 49,000 out in front. And then on the inside, we'll FOIL. We'll have a leading term of minus y squared. The middle term is the inner and the outer are going to cancel, though. We're going to have a minus 7y and a plus 7y, which will cancel, and then a plus 49. So that'll be our simplified integrand when we FOIL. And then we'll integrate that part. And we're going to get minus y cubed divided by 3 plus 49 times y, 0 to 7. So here we're going to have minus 7 cubed divided by 3 plus, do you see that 49 is 7 squared, and we're going to multiply it again by 7, so we have another 7 cubed over there? And I'm only going to do it that way. If I was doing it by hand, this would make it a little simpler, because then I could factor out the 7 cubed. And then we can factor out 7 cubed. And if we factor out 7 cubed, we're left with minus 1/3 plus 1, which we can do in our head. Minus 1/3 plus 1 is 2/3. So we have that. But then we're going to have to type into a calculator anyway, because that's pretty hardy multiplication. So is there any part of that that is driving you nuts? Seven cubed. That's not 7 cubed. And then multiply by 2/3. Doesn't like something. Oh, it doesn't like that thing.
7 times.
7 times a flying 3? Yeah, it's not going to like that. So that is our answer. And what are the units then? Yeah, so we're finding work. Work is a Newton meter or a joule. And you can use either. Does not matter. So we'll put a big J over there. And I should have done it. Usually we want, that's an approximated answer. It's always better to use an exact answer whenever possible. So if it doesn't ask us to round, we shouldn't round. So we should actually leave it like that. That is our preferred answer. We don't want to round unless the instructions say to round. We shouldn't round, so we're going to do that.
On your example, you asked for scientific notation or anything?
I won't ask for it, but you can use scientific notation if that's your preference. Yeah, the only thing that you would not want to do is round. Just don't round, unless it says to round. So if it doesn't say to round, you should leave the pies in there, leave the square root of 3's in there, leave the fractions in there.
Where did the negative and the negative y cubed over 3 go?
That negative?
Yeah.
So when the 7/3 is factored out, 7/3. When the 7 to the 3 is factored out, we have this. If we factor out 7 to the 3, we're left with 7 to the 3 comes out of here, we're left with minus 1/3. 7 to the 3 comes out of here, this is over 1. So we're left with a 1, and then 1 minus 1/3 is 2/3.
Could you scroll up a little bit?
Yes. Is that far enough?
Yeah.
All right, is there, Hayden?
Sneaky perfect square trinomial.
Sneaky perfect square trinomial. So arc length, is that one the sneaky one, do you know? I didn't write it up there. How did I not write it up there?
Sneaky.
Yeah, which one is, this one looks like it could be sneaky. That one, well, they both could be sneaky. Let's try this one first. How do we know if it's going to be that perfect square trinomial thing? You remember?
We should end up with the same thing but a different sign.
Yes, exactly. So when we add 1, when we're doing the arc length thing, we have the derivative squared plus 1. And when we add the 1, we're going to end up with the same trinomial, except that the middle term will have a different sign. So let's check. We can do it pretty fast to check whether it's going to be one of those things. Normally I would warn you. I don't know why I didn't warn myself. Okay. So find the arc length of this curve on this interval where y is going from 3 to 4. So we know that we're going to have a derivative here. So let's find the derivative. So the 4 comes down, and it's going to cancel with that 4, so we're going to get a y cubed. And maybe it's helpful to rewrite this. The common mistake I see here is that the 8 is not treated separately and kept in the denominator. So that 8 is in the denominator. And when we take the derivative here, we get minus. So 2 over 8 is 1/4. And we subtract 1, we get y to the negative 3. So we get that. And so we know with arc length or surface area, we have to do that ds conversion to dx or dy. So we have to square the derivative here. And here's the part, if we're doing arc length, that I recommend don't just FOIL it all out and simplify everything. Leave it in its general form. That's going to make your life easier in the long run. So when we square this, we get that. And the very last term, that's an easy term, so we're going to have plus, when we square all this, 1/16. Oh, but let's not, it's so tempting, right? It's so tempting to multiply it out. Let's just not multiply it out. So this is generally referred to as A. This is generally referred to as B. And when you take A minus B and you square it, you get a squared minus 2ab plus b squared. So we've done the a squared and the b squared. Now the part that we do want to simplify is the middle. So the middle is minus 2 multiplied by a multiplied by b. So that part, we know if that middle simplifies to negative 1/2, that's going to be the sneaky perfect square trinomial, because if you add 1 to negative 1/2, you get the positive 1/2, so then you've only changed the sign of the middle term. So let's see what happens. So the first term and the last term we're not going to do anything with. Negative 2 times 1/4. Okay, that's negative 1/2. And y cubed times y to the negative 3 is 1. Y cubed times y to the negative 3 is y to the 0. Y to the 0 is 1. So this is perfect square trinomial. And so when we do our next step, we have x prime squared plus 1. When we add 1, if you add 1 to the right-hand side, that changes that middle term from a -1/2 to a +1/2. Which means that we can then go to, if we look at this, so that's where we're at now. So we started with a minus b, we squared it and got that, then we added 1 and got that, so this whole thing is going to equal a plus b squared. So a is y cubed plus b, which is 1/4 y to the negative 3, quantity squared. And then the integral is going to be really, really manageable. Yeah, it's always, doing a few of these, takes a few of these before they start to feel easy. So arc length, we'll use a little s. Now, we are integrating with respect to y, so we need y limits of integration, which they gave to us, 3 to 4. So 3 to 4. And remember, the formula is 1 plus x prime squared times dy. So now we're just plugging in that formula, or plugging that function into this formula. So we have integral from 3 to 4, square root. 1 plus x prime squared is all of this. Well, of course, the square root undoes the square, so we just end up with the integral of a polynomial. Oh, well, it's not a polynomial because there's a negative exponent, but integral of something that is integrated like a polynomial. Polynomials have to have non-negative exponents technically, though. So then we can do our integration. So here we're going to add 1 to the exponent. It's a negative number, so when you add 1, it becomes less negative. So we're going to get y to the negative 2 divided by negative 2, so that's going to become negative 1/8 in front, 3 to 4. And a couple of things you should be checking. All right, so that quantity right there for your x prime should be exactly this, except the sign is converted. And that should look really familiar also. It looks almost identical to the original function. So there's a few places that you can check that you're not going off track if it's one of these trinomial ones. But you still have to show your work. Still must show work. Plug in the 4. We get 4 to the 4. There's a 4 in the denominator, so we really have 4 to the 3. So 4 to the 3 is 4 times 4, which is 16, times 4, which is 64. Minus 1 divided by, so 4 to the 2 is 16, but it's in the denominator. So we have a 16 multiplied by the 8. So 16 times 8 is 128. And then we subtract off antiderivative evaluated at 3. So we get 3 to the 4th over 4. 3 to the 4th, 3 times 3 is 9. 9 times 9 is 81, so we get 81 fourths. And then minus a minus is plus. 3 to the negative 2 is 1 over 9. So we end up with 1 over 72. That's our step, our penultimate step. Our step before we finish. That's not what I want.
Fill that out.
Some steps in the middle that I'm not quite getting.
Henry, did you say there was a step in the middle that you wanted to ask about?
Yeah, there's, let's see, you go from x prime squared, you got, a squared plus 2ab plus b squared, you got that sort of formula going. And then right underneath that, you have x prime squared plus 1, and then you just have these little, what look like parentheses marks all over the place, or a couple of them. And then, yeah, I'm
So
just-
these just mean that you're bringing this right down. You're not doing anything to it.
Oh, okay.
So it's just a quote that we use that notation to represent not doing anything, just copying that same thing over.
Okay.
So
What's
y to the 3 squared.
where does the plus 1 come from?
That's from our formula for arc length.
Okay.
So our formula for arc length says that we have S equal to the, so our general formula for arc length is right here, square root of 1 plus x prime squared. That's our formula for arc length.
Okay.
And so over here, once we have our x prime, we square it and then add 1 so that we can then fill it into the inside of that square root,
Okay.
inside the root. All right, another topic. Should we do a force one? Oh, Sam?
Wouldn't it be minus 1/72?
So remember that we take this whole antiderivative thing, and we take antiderivative at 4, which is right there, and then we subtract off the antiderivative at 3. So when we subtract,
so you just,
we
okay.
distribute that minus. So that's going to force it to be plus in the end. Make sense?
Got it.
Zach?
What up?
Looks like you have a puzzling look on your face.
Maybe, but I don't know what I was thinking about.
Probably not math then. Dreaming of work?
Maybe.
All right, any other piece of this you want to ask about? And again, there's the video there too if you want to re-listen to it, or you try to, if there's a part of it that is not making 100% sense. So we did, let's do force. We already did a trapezoid with the work one, so maybe we'll do the circle for this one. Let's see if we can get through the setup on this pool problem.
Which problem is this?
So this one is the second of the force problems down here, so 6, 7, 54. Okay, so force is two-dimensional. So we're going to have a two-dimensional expression here. Versus work, where we have a three-dimensional tank, we have a three-dimensional quantity there, volume. So if it's force, so force on a window, force on a dam, it's going to be ADD area. So big picture, ADD is units of pressure. So pressure is force per unit area. And if you took force per unit area and multiplied by area, the areas would cancel, and you would get whatever these units are over here. So ADD is force per unit area. The areas cancel, you end up with units of force. So that matches. That's what we're trying to find, units of force. So newtons, the cumulative newtons pressing against that wall or that window or the dam, whatever it is. So we're going to use ADD area. This pool is 8 meters deep, filled with water, and we've got a circular window here that's got a radius of 2 meters. So I'm going to draw, the pool with I'm thinking of the coordinate system down here. So there's the x-axis, there's the y-axis. So the equation of that circle is shifted up so that its center is at 0, 2. So let's focus on that for a minute, on the equation of the circle. So the equation of a circle at the origin is x squared plus y squared equals r squared. But if it's shifted, it's not shifted in the x direction. It's x minus 0 squared. So x minus 0 squared. The y part is y minus 2. So this is shifted up 2 units. And then the radius is 2, so squared radius on the right. Now, like we've seen several times when we're dealing with these problems with fluid, we need a horizontal representation because it's at that horizontal level that we have constant pressure, right? A constant pressure at that same horizontal level. And so we're going to need to take whatever the equation is for the circle, and we're going to isolate x so that we can measure sideways. We can measure horizontal. We can find the distance over to the right edge of the circle. So I'm just isolating x here. So subtracted off the y expression, and then took the positive square root. So I'm looking into quadrant 1 up here where x's are positive. The whole right side of the circle, x is positive. So this is going to be the right half of the circle. Okay? And if you FOIL this out, y minus 2 squared, and collect the like terms, it simplifies to what I have there. So that x is measuring from the vertical axis over to the right edge of the little circular window. So if we are going to go all the way across here, all the way across is w, what are we going to do to that x there? Double it. So that's what we're going to do to get to w. All right, so let's just write that down first. So w will be 2 times the square root. So that will be w. All right, so now let's go to our acronym. So again, ADD area for force, ADD volume for work. Which also makes sense because force times distance is work. So if we tossed in another unit of length, we would end up with force times distance, which would bring us to work. All right, so acronym, ADD first. Acceleration, density, depth. The tank is 8 meters in total, so if we do this complementary distance, that's going to be 8 minus y. Bless you. All right, this distance right here is y. Y takes you from the bottom, from the x-axis up. 8's all the way up, so 8 minus y is that complementary distance right there. So that's what that is. And then w, right here, right there. And then w is a width. And if you multiply that by dy, you're getting the area of the strip. Not the area of the circle, you're getting the area of this rectangular strip. So you're thinking about this little strip now, you're adding some thickness to it, and that thickness is your dy. So w multiplied by dy gives you area of that tiny horizontal strip. So this is area of strip. So that's where we're at then. And that's our setup for this. Now integrating this is going to be a little tricky. We're going to just stop here at the setup because the integral of that's a little extra work.
Oh, so we, okay.
So this one we're just doing a setup. So if I give you one of these circles, either I'm going to ask you for the setup,
I'm like halfway.
or it's going to be cooked up so that you could use U sub in a pretty easy way.
And then the limits of integration are just like, that's just the height of the window, right?
Correct.
Okay.
So whenever we're finding the limits of integration, they need to reflect the physical quantity that we're dealing with. So we're trying to find the force on this window. So we want to look at wherever water is pressing and exerting a force on that window. So we're finding the force basically at each strip and then adding them up. And so we have force happening at all these strips of window between 0 and 4. Yeah. So it's actually the physical location of the window. So 0 to 4. All right. Let's look at the other force problem also. This one is easier, so let's just take a look at that. And the numbers are more manageable. The last trapezoid we had some fractions, which can be a little bit, they shouldn't be, but they are a little bit overwhelming to everybody. Doesn't matter how much math you've done in your life. When you start seeing fractions, you start thinking like harder than you probably need to, but you just do. So another one, we've got a trapezoidal dam. We want to find the force on it. Trapezoid has 4 as the upper base, 2 as the lower base, and the height of the dam is 3. So again, we're going to use our ADD area acronym. And it's just shocking how simple this is. You don't have to think about all these complicated pieces of it. You just fill in the blanks, which is pretty cool. So we have 9.8. And then the more you do it, the more you start thinking about the units. And it all starts to make sense. If you look carefully at the ADD, you get units of pressure, which is force per area. The areas cancel, you get units of force. So the second D. When we're looking at that second D, we're looking at the depth of our representative strip at Y. And that depth of that strip is? So the height of the dam is 3. So 3 minus Y will be our... I know, it's very easy to grab the wrong number. So there's ADD. And now area, again, it's not area of the dam, it's just area of this little strip right there that's got a thickness of dy. Okay, well the area of that is going to be W multiplied by dy. It's going to be whatever the width is multiplied by that tiny thickness. Okay, so let's deal with this trapezoid again. All right, we did this already. The easiest way to find the equation of that right edge is to use the point slope formula. So we need to know the coordinates of each of those points. How about that lower right point? 1, 0. Everyone okay with that? We're imagining our coordinate system halfway in between, right there. So 1, 0. And how about that upper number? 2, 3. Good. So the upper base divided by 2, and then the height is 3. So that is those are our 2 points. And it doesn't matter which point we use. Let's use the harder point this time just to mix it up. Doesn't matter which point we pick with point slope. So let's do y minus 3 equals. And then we do rise over run for slope. So we're at this point. We go up 3, and how far over do we go? 1. Yeah. It's so easy to. So everybody see that? We're gonna go up 3. That's the easier part to see. We're gonna go up 3, and then we're gonna go over 1, because this whole thing up here is 4, so half of it's 2, so half of that is then gonna be 1. So we're going up 3 over 1. And then we chose to use the other point, that one, so it's x minus 2. Doesn't matter which point you pick. So let's clean this up a little bit. So y minus 3 equals 3x minus 6. We want to isolate x. So I'm going to isolate the 3x. So I'm going to add 6 to both sides and get a y plus 3. And divide by 3, we'll get a third times y plus 1. How do we get W from that?
Double.
Double it. So that x is measuring from the vertical axis to the right. We want all the way across, we have to double that. So we're going to double that. Double that, we get 2/3 y minus plus 2 times dy. Limits of integration? Zero to 3. So we look physically where the water is putting force on the dam, and that's from a height of 0 up to a height of 3. So that is our setup. And we'll just get the setup's enough for this one. Factor out your constants, FOIL, and integrate. All right, let's take our 10-minute break. And if you have any questions, I will be lingering around. Hey.
In this specific problem, could we put the depth as y? Is it 3 minus y? Or would that not work?
It will. So power reduction identities for sine squared and cosine squared, those are ones that we've done, but you don't need to know the ones for the hyperbolics. So sinh squared and cos squared, you don't need to know. So the only hyperbolic stuff we need to know are the ones for
Integral and derivative.
derivatives and integrals. Yeah, derivatives and integrals. Those are the only. That's all of 7.3. Should we do some 7.3 just to get that out of the way?
Yeah.
So the hyperbolics derivative here. The common mistake here is to not do the chain rule properly. If you have any inclination to mess up the chain rule with trig functions, then it might be better to rewrite this as sinh 2x quantity to the 4th. Okay? Then the chain rule is a little bit more obvious, that you have to take the derivative of the base. So with an exponential expression, we call this the base and that the exponent, and so the base has to be differentiated. So if you have any tendency to make a mistake with this type of derivative, rewrite it. And then this becomes sinh of 2x cubed. You bring the power down, subtract 1, and now it's a little bit more in your face that, ooh, now we need to differentiate the base. The derivative of sinh is cosh. And then we have to differentiate the angle and get a 2. So when all is said and done here, we're going to get minus 8. And we'll go back to that shorthand notation. So we would get that as our derivative. And that makes sense? Kind of straightforward. Another derivative. So here we have a natural log function. And the first thing with a natural log is 1 over the inside. That's our first step. Anytime we have a log derivative, so f prime, we start with 1 over the inside. So 1 over cosec of 11x. So 1 over the inside multiplied by the derivative of the inside. So a couple of things to think about. When we are talking about the derivatives of the hyperbolics, we have the primary 3, sinh, cosh, tanh. Sinh, cosh, tanh. Those all are going to have positive derivatives. And then the other 3 are going to have negative derivatives. So we know this one's going to be negative. Bless you. And we can probably see that we're going to have to take the derivative of that angle and multiply by 11. Also, so we can put that out in front if we want to be proactive. And then we have to differentiate cosec. Cosec will differentiate just like cosecant. Derivative of cosecant is minus cosecant cotangent. So the derivative of cosec will be minus cosec cotanch. So minus cosec of 11x cotanch of 11x, and then multiplied by 11. And then we have a little bit of cancellation. We have a cosec 11x in top and bottom. So this will all reduce to minus 11 cotanch times 11x of 11x. We look at an integral. Integral of that. Any ideas? You don't have a lot of integration techniques. What do you think the technique might be here? You got nothing? Yeah. Natural log? Yeah. So the underlying principle would be U substitution. But we have a situation, we know that if you do have U substitution, picking your U properly, of course, is a little tricky sometimes, but it's usually what's in the parentheses somewhere. So it's inside the angle, it's inside the exponent, it's inside the square root, or in this case, it's inside the denominator. But what we notice is that the denominator's derivative is the numerator. And that's our shortcut. That's log form. Anytime the derivative of the denominator is the numerator, you can cut right to the chase. Now, if you didn't see that, and you let u equal 19 plus cosh of x, that's totally fine. This will come out absolutely fine. When you differentiate here, the derivative, you get sinh of x multiplied by dx, and your integral is going to become the integral of du over u. Right, the numerator, sinh times dx, that's du, and the denominator is u. So we get du over u, and the integral of that is natural log absolute u, which will be natural log absolute 19 plus cosh plus c. And that would be our answer. And here, because cosh is the hanging cable, it's always above the x-axis. You don't really need the absolute value bars. So if you have them, it's totally fine. It's not wrong. But if you wanted to go as simple as possible, you could take away the absolute values on anything that's already positive. Don't need them on anything positive. But you can cut straight to the chase right there. Anytime it's in log form, you can just cut to the chase. So let's take a look at this integral. So the only things from the hyperbolics you need are the derivatives and the integrals. If there's an identity, I would give it to you. If there's some identity that's necessary, I would give it to you. So in this case, we're going to end up with the integral of 1 minus sec squared of x. The integral of 1, of course, is just x. And then where are we going to go from there? So it should parallel a little bit. Sam, do you see it?
Isn't it tangent?
So tanh. So derivative of tanh is going to be positive, first of all, because it's one of those first three. Sinh, cosh, tanh all differentiate to positives. Derivative of tanh is going to be sec squared. So this will be x minus tanh of x. Yeah, good. Sense to everyone? Pinch. Pinch. And one more integral. I guess this is one, well, how do we rewrite tanh in terms of its reciprocals? Sinh over cosh. So it's the same as tangent, but it's with the hyperbolic. So sinh over cosh. And then this has limit. This is a definite integral. So we have that. And then how does that integrate?
The natural law of
So log form, LF, that's in log form, so we're going to get natural log of the absolute value of the denominator. Once again, you could say, oh, denominator is a hanging cable. That's always above the x-axis. We don't really need the absolute value bars. So for us, we would rewrite this as, when we plug in, we're going to get cosh of natural log of 10 minus cosh of 0. And what is cosh of 0? So cosh of 0 is 1, so we would replace the cosh of 0 with that. Now on the homework, and again, I'm not going to ask this on the test, there is a way to simplify cosh of natural log of 10 if you go to the definitions of cosh and sinh. The definition, so the definition of cosh is the thing that uses the exponential functions, where we average exponential growth and decay. So that is the definition. If someone says, what's the definition of cosh? You could say, it's the hanging cable. But the mathematical definition is this, where you average exponential growth and exponential decay, and that gives you the hanging cable. And so if you use this definition of cosh, and you plug natural log into each of these positions, you could simplify. E to the natural log of 10 is 10. But I won't ask you to do that on the test. But in the homework, where you have access to all the extra formulas, you should be able to do it. Yeah?
Why is the cosh ln of 10 minus 1 inside of the parentheses for ln? Why isn't it just ln cosh of ln 10 and then minus 1?
I think I misunderstood. Let me. So do you agree with this step?
Yeah.
Okay, so then we're going to plug, this is our upper limit, it's going in there. And then this is our lower limit, and it's going to go in there. And cost, so it's, oh, I understand what you're saying. Great question. Does everyone see the bad math that just happened in front of your very eyes? Do you see the bad math? So it's the antiderivative evaluated at this minus the antiderivative evaluated at that. Everyone see that? So I kept the log on the outside and just treated this as the antiderivative. So that's not right. Good catch. So right in here, this minus part here should be the entire antiderivative. So we don't even need, well, I guess we can keep that there. So then it's minus natural log of cosh of 0. Nice, thank you very much. Okay, so it's that. And then cosh of 0 is 1. And what's natural log of 1? 0. Yeah, so this would be, this should be our correct answer if we don't go ahead and do that piece. Yeah. Nice catch. Okay, so that's the extent of the derivatives and integrals that you'll need to know for the hyperbolics. We don't spend a ton of time on them. They come up periodically. The main thing in your mind is that they parallel the circular functions. and the derivatives and integrals are closely related. So when they come up, you should be able to manage them. All right. We definitely should do some volumes. And let's first do a volume by slicing. So there's going to be a generic, they call it a general slicing principle. So the general slicing method. And this one says that we want to, so here we're geometrically creating the solid object. We're sort of identifying the cross-sectional shape and saying stack a bunch of those next to each other to create this solid object. We're not using rotation. So we're not building it with some sort of mechanical process. We're just identifying the cross-sections and building it. So we want to find the volume of the solid that has this base. So we're talking about the base of the solid. The base of the solid is created by these points right there. So we've got this triangle. That's the base of our solid. So the solid is coming straight out of the board. Okay, and a couple of you made this mistake on the worksheet. We've got to be very careful with how they describe the cross sections. So the cross sections here, perpendicular to the base is meaningless in terms of what we are going to do. It just means they're coming out of the board right at you, perpendicular to the base. All right? That part can seem extraneous and confusing, so just remember that all of our cross sections are perpendicular to the base. If they weren't perpendicular to the base, you'd have a very complicated situation if they were coming in at some oblique angle. That would be very hard. Like our cross sections are, when you think cross section, you think perpendicular. So that part is kind of extraneous. Here is the important thing that a couple of you missed on the worksheet. So parallel to the y-axis, there's 4 ways this could be stated. You could go parallel to y, parallel to x, perpendicular to x, perpendicular to y. So parallel to y and perpendicular to x would be the same direction. Parallel to y, perpendicular to x. Or if it said parallel to x, they could also say perpendicular to y. So there's 4 different ways that might be stated. So as soon as you see that, parallel to y, your integration element or your sample rectangle is that. Parallel to y or perpendicular to x. Should go that way. All right, so now we have the integration variable identified. Now we know we're going to integrate with respect to x. We're going to use a dx. So we have that. And this is a generic vertical element at x. All right. And now it tells us what the shapes are. So the shapes are semicircles. So we're envisioning all of these semicircles that are kind of stacked next to each other, coming straight out of the board like that. So it's kind of like half of a skewed birthday cap kind of thing. So those semicircles are coming straight out of the board. What we need to identify is the radius of each semicircle, because the radius is what's going to dictate the area of a semicircle. The distance from the x-axis up to that diagonal line is going to give you a diameter of the semicircle, not the radius. So the radius is going to be halfway up. So we know that the area of a semicircle is going to be pi r squared, that's the area of the full circle, divided by 2. So that's our generic area for a semicircle. So now we've got to figure out what the radius is as a function of x, because we're going to have a dx. So we're going to want to turn that r into some expression that has x's in it. All right, so let's find the equation of this line right here. We can again use point slope. We've got 2 points on this line, so we could use point slope. It's a little easier though, because we actually know the y-intercept and we know the slope, so we could just use slope-intercept form. So we know y is equal to the slope, which is -1. So So negative 1x plus the y-intercept is 2. And if we used point slope, you'd get to the same exact place. Does not matter. So now we have the area of our semicircle. If we convert it into an expression with x's, we're going to have this radius squared. That'll be the function that we're going to integrate. That is the area of the semicircle at x.
It wouldn't be that over 2?
I just put the over 2 there. I just moved that as the coefficient out in
No,
front.
but for the radius, like is negative x plus 2 not?
Oh, shoot. Yes. Thank you. Yeah, let's. Man, blowing it. So the radius, this is the diameter. So over 2. So yes, we should have it over 2 right there. Thank you. Right. Yeah, that thing is the whole diameter, right? That goes, if we go all the way to the diagonal line, that is the diameter of the semicircle. So we do have to divide that by 2 to get to the radius. 100%. Totally agree. Now we can kind of square this out. We get pi over 8. So the 2 in the denominator here gets squared, turned into a 4, and we can pull it out to the front. And then here we're going to have an x squared minus 4x plus 4. Look at that. And so this next thing I'm going to point out is where I would have noticed my mistake. When we use this, if we think about this as the area of the semicircle and we check our 2 extremities, if we plug in x equals 2, we get 0. And even with my mistake, I still would have gotten 0, so I wouldn't have known that there was a mistake yet. But then checking the left extremity, what is the radius of this circle here?
1.
1. So the area of that semicircle should be pi r squared divided by 2. So it should be pi times 1 squared over 2. So it should be pi over 2. Well, let's check. If we plug in 0 here, do we get pi over 2? We plug in 0. We get 2 over 2, which is 1. 1 squared is 2, so we get pi over 2. So that is right. Whereas with that out the division by 2, I would have noticed that we had the wrong area there. So if you always check your extremities, that'll tell you whether your generic formula is correct or not correct. So what do we do to that area function to get the volume then? Plug it into the integral, and then our limits of integration will be from 0 to 2. So our volume will be the integral from 0 to 2, and that 0 to 2 is from the x-axis, not the 0 to 2 from the y-axis. That's coming from the x-axis. Our interval of integration is down here. That's where we're integrating, 0 to 2. Pretty easy integral. You can watch the video if you want to see the exact answer at the end. So generic slicing method. So you're constructing the solid object by identifying geometric cross sections. Let's compare that to, let's do a washer problem, since that's just a glorified disk. Washer is really 2 disks. So find the volume of the solid generated when the region bounded by these 2 functions is revolved around the x-axis. Okay. So the axis of rotation here is horizontal. Right, there is our axis of rotation. And we are going to use washers here. So on the test, I will ask you to use either a disc, a washer, or a shell. So you want to use whatever you're asked to use, even if you could do it a different way. If it says use washers, use washers. If it says use shells, use shells, if you want full credit. So when we draw a representative rectangle here, should it be parallel to x, to this x-axis, or should it be perpendicular to the x-axis? Perpendicular. Right, perpendicular, if I draw that element right there at a random x, that's what creates a washer. Right, it's got to be perpendicular to the axis to create a washer. If it was parallel to the axis, it would create what shape? A cylinder, right? Right? If it's parallel, it's creating a cylinder. If it's parallel to the axis of rotation. But perpendicular, it's going to either create a disk or a washer, depending on whether the region is touching or not touching. All right, so there is our generic rectangle element, however you want to think of it. So then we have to identify the outer radius and the inner radius. And so the distance to the closer curve from the axis of rotation, that is the inner radius. The inner radius is from the axis up to the first curve. And then the axis up to the second curve, the further curve, that distance is the outer radius. Our first task is to find the area of a washer, which is going to be pi times the outer radius squared minus the inner radius squared. So that's a washer. Pi r outer squared minus pi r inner squared. Factor out the pi. So big disk minus small disk. Are we going to have a dx or a dy here? Dx, because we have a vertical rectangle, the thickness is dx. So we have a vertical rectangle. So that tells us that we need to turn the r sub o and the r sub I into x's. So we should have x's. So let's see. So r outer squared. So r outer squared is this red one. It goes up to that curve. So r outer is that function. So 32 square root x. And that quantity is squared. Minus r inner. That's the blue one. It goes up to this one. So 8x quantity squared. Yep.
If we didn't have the visualization, how would we find which one's outer and which one's inner?
If you didn't have, I would recommend if I don't present the graph to you, I would recommend graphing it so that you kind of have a sense. You could, if I give you the two curves and tell you what the, where the limits are going to be based on
And you
whatever,
plug in a number in
you could see which one's further away. Yeah, you could do that. Ideally, you'll be able to graph them though. So you should be able to graph basic exponential functions, basic polynomials, and parabolas. Nothing crazy though. So then we square this out, and I don't know what 32 squared is. Can someone figure out what 32 squared is?
124.
Yep.
Did you say 1024?
1024.
1024, thank you. So that is going to be our simplified washer area. And if you plug in either of your extremities, you should get 0, because these things pinch off on both sides. We haven't found the limits of integration yet, though, so we need to know where these two curves are intersecting. So let's go ahead and do that. So the intersection points will set the two curves equal to each other. So 32 times the square root of x equal 8x. We can certainly cancel out an 8 on both sides first. So divide out the 8. When you have a square root, generally the easiest way to solve a square root equation is just to square both sides. It's usually the easiest way. You can put everything on one side and factor out a square root if you're comfortable factoring square roots. Usually most people are more comfortable squaring than factoring square roots. So if we square both sides, we just have to remember we might introduce extraneous solutions. So if we square both sides, we have that. Square both sides. And then we put everything to one side and factor. move everything to one side. Factoring here is quite simple because the only thing that we can do is factor out an x. And then we apply the so-called zero product rule. The only way a product can be 0 is if one of the factors is 0. At least one of the factors. So that tells us that we're at 0 and 16. So we're going to integrate across from 0 to 16. So there's a washer for each of these representative rectangles from 0 to 16. And if we plug in 0 or 16 here, we should get 0 for the area of the corresponding washer. So if you plug in 16 right there and square it and multiply it by 64, 16, you should get 0, which you can check if you have any doubt. So the volume will be the integral of this area function with respect to x from 0 over to 16. So our antiderivative will be 512 times x squared minus 64 thirds times x cubed from 0 to 16. And you can plug in the 16. Plugging in 0 gives nothing, so if you plug in the 16, you would get your final answer. Thanks, everyone. So let's definitely do a shell, unless someone has a question on that guy. All right, so shells tend to be the more complicated thing, so let's do shells for sure. So use the shell method to find the volume of the solid formed when a hole of radius 3 is drilled symmetrically along the axis of a right circular cone of radius 6, height 9. So we've got a cone, radius 6, height 9. We're just going to take a drill and drill out the middle, whatever, of radius 3. It's going to be like a cylindrical type of boring. So let's first draw our cone. We'll draw it as a triangle, a little easier to visualize. So the height of it is 9, so we're there. The radius of this cone is 6. So this distance right here is 6. And then we're going to take our bit and come straight from the top and drill out a radius of 3. So we're going to drill out and remove all this stuff. All that stuff's going to go away. Everyone with me? So all that stuff's gone. So we want to find the volume of what's left. So we want to find the volume of this. And I've just taken a cross section, right? I've just taken a two-dimensional cross section. Really that one of those orange things you can imagine rotating around the y-axis to create what's left. So we're going to have whatever that shape's called. Probably doesn't have a name. A bored out cone. Okay, so let's see. This, when we drill out this thing here, it's radius 3. So there is going to be a 3 right there. And I'm thinking of the origin as being right in the middle here. So we're imagining our coordinate system right there. And we're just being left with the material that's from 3 out to 6. Okay. So the axis of rotation is vertical here. We're rotating around that vertical line. And should we draw our representative rectangle vertically or horizontally to create a shell? Vertically. So our representative rectangle at x has to be parallel to the axis of rotation to create a cylinder. Perpendicular, it would create a washer. We could probably do this with washers too. The washers are stacked horizontally. Probably could do it with washers. But we are dealing with nested cylinders, cylindrical shells. So we first are going to find the area of a representative cylindrical shell. So that's 2 pi RH, circumference times height, 2 pi RH. And then we have to come over here and identify H and R, all the things. And let's see, so this distance from the axis of rotation to our representative element, that's called R. And then height is just the height of our representative rectangle. What letter should we be integrating with respect to?
Why?
Try again.
X.
Yes. Do we see why it's x? So if we have a vertical element, how thick is this vertical rectangle? So that vertical rectangle is dx thick. A horizontal rectangle is dy thick. So if we have a vertical rectangle, it's dx thick, that means we're going to integrate with respect to x. So one thing you could think about is that anytime you have an integration with a representative rectangle, that's always going to be perpendicular to the axis that you're integrating with respect to. All right? So if you have a vertical element, you're going with respect to x. Remembering that a vertical element is dx thick, that's another clue that you should use dx. So that tells us that we want to turn the r and the h into expressions that are x's. So let's look at the r first. So r is the distance from the axis over to your element. And what is that distance from the axis to the element?
X plus 3.
X.
X. All right, so let's make sure we understand that. I heard a couple of other options. So 3 gets us to the edge of the hole that's bored out. So the axis of rotation is this green axis. The limits of integration will be 3 over to 6. Right, this is 6 over here at the boundary. The limits of integration are definitely going to be over here because there's going to be a cylinder for all of those x's between 3 and 6. If we think about the definition of the radius, if we put our vertical element there, the radius is the distance over to that vertical axis. But that's the same definition as a random x. If we just put a random x, that means the distance from the vertical axis in your coordinate system. Right? Whenever we draw a vertical element and label it as x, that means we're x units from the axis of rotation, as long as we're to the right of the axis of rotation. If we're over here, it would be the absolute value of x. But if we pick an x over in quadrant 1, that's how far it is to the axis of rotation. So that is r. So this is r. And then how about the height?
So we need the equation for that right line right there.
Correct. So we need to take these 2 points, form the equation of the line that connects them, and that will be the height.
Is it going to be a y equals something?
Yep.
Okay.
So what is this y-intercept here? 9. And that horizontal distance right here is 6. So the slope is negative because it's going down. And the rise over the run, it's going to be 9 over 6. So the slope will be negative 9 over 6, which is negative 3 over 2. So the equation will be y equals negative 3 over 2, that's the slope, times x, plus the y-intercept is 9. Or you could do point slope. If you're not good with slope-intercept and you're not seeing that, just do point slope. This point up here is 0, 0, comma 9. This point down here is 6, comma 0. You can just do point slope. Excuse me, you could just do, yeah, point slope. That's what it's called, point slope. No, that's not what it's called. What is it called? Is it called point slope?
Yeah.
Yes, it's called point
So, I
slope.
mean,
That
you
sounds
find
familiar.
the slope first and then do point.
Find the slope and then do point slope.
You're
Yeah.
asking someone who hasn't heard that term in like 16, 17 years.
So point slope is the y minus y1 equals m times x minus x1. That's point slope. That one. So point slope will always work, but our shortcut, because we know the y-intercept, is to use this thing. Slope intercept. Thank you. Slope intercept. That one. Slope intercept. Does everybody see the slope is negative 3 halves? Because you're going up 9 over 6, so that's 3 over 2. Okay, that is our height. Negative 3 halves. So please study very hard. Make my grading easy this coming weekend. It's so much easier to grade perfect tests. Somebody please be the answer key. Who's going to nominate themselves to be the answer key? So then we can distribute this x. And that is the area of the cylinder at x. And we got a whole bunch of cylinders nested between 3 and 6. So that will reflect our limits of integration. Volume will be the integral. We can factor out the 2 pi. We'll integrate from 3 to 6. Minus 3 halves x squared plus 9x. And if we integrate here, we get minus 1/2 x cubed plus 9 halves x squared from 3 to 6. Plug in our limits of integration. So plugging in 6, we're going to have 6 times 6, which is 36, multiplied by 3. Or I think that's negative 108. 216 divided by 2 is another way to think of it. And then here we have 36 divided by 2, which is 18 times 9. Is that 171? Somebody check.
18 times 9 is 162.
Okay. Not even close. 162. Random guess. All right, so minus. Now here we have to be careful because there's this negative here. So when we subtract off, we're subtracting off all of this evaluated at 3. Minus a minus is going to turn into a plus. 3 cubed is 27 over 2. But then this one will be minus 9. So that'll be 81 over 2. So that will be, then we just have to plug and chug it with your calculator, unless you're good at arithmetic. Not you. I want that. All right, minus 108 plus 162 plus 13.5 minus 40.5. Fraction. Oh, it's not going to let me do a fraction? Oh, because it's an integer. I can do a fraction there. Okay, so we end up with 54 pi. 27 multiplied by 2 pi. 27 multiplied by 2 pi, so we get 54 pi. Oh yeah, that's good. It's an even number. All right, any questions on any of the setup there? Let's do everyone's favorite, random access. So random access, you really have to have the concepts down in order to do the random access right. So the first thing, so this is a good example of things that I would expect you to be able to draw and create. So we're going to have y equals x squared, x equals 1, y equals 0. So y equals x squared. X equals 1 is a line at 1, so something like that. Let's just get a sense of what the shape is first. Y equals 0, that's going to be this direction. Y equals 0. Okay, that's it. So there should be no ambiguity. So this is our shape in there. That is our shape. That little triangle-ish thing. All right, and we're going to rotate around line out here at -7. So that is our axis of rotation, -7. And it says to use the shell method. So will we be drawing a vertical or a horizontal rectangle in there? Vertical. It's got to be parallel to the axis of rotation. So that is a random vertical rectangle at x. We are creating a cylindrical shell, and the area of a shell is 2 pi rh. Are we integrating with respect to x or with respect to y? X, right? Vertical rectangle, thickness of that vertical rectangle is dx. So integrating with respect to x. So the r and the h have to turn into x's. What is r?
X plus 7 plus x.
Yeah. Everyone see that? 7 plus x? So if you are looking at this, you can think of it geometrically. If you think of it geometrically, this distance from there to there is 7, distance, 7. And this distance from here to right there, right at that x, well, that distance is x. X is positive, right? It's in quadrant 1 over there. So the total distance is x plus 7. If you wanted to go back to one of our founding principles, horizontal distance is right minus left. The right x is x, the left x is -7, so x minus -7 would give you x plus 7 also. So a couple ways that you can convince yourself that that distance is x plus 7. And then how about the height of that rectangle at x?
X squared.
X squared, yeah. So that is our area function. So then our volume is nothing more than the integral of the area function. So we're going to integrate x cubed plus 7x squared with respect to x. And that's going to go 0 to 1. Yeah. That right vertical edge of our rotated region The region that we're rotating is over at 1. So that'll be our setup. We can blast through this integral. We get x to the 4th over 4 plus 7x cubed over 3, 0 to 1. So we get that. 0 is going to create no volume. So we just have to plug in the 1. Common denominator of 12. That one we multiply by 3 over 3. That one we multiply by 4 over 4. Whatever that is. The top of that is 31 times 2. Oh, 2's canceled. So 31 times pi divided by 6. That'll do it for us. Any part of that? Hopefully it's starting to gel. Starting to see all the shapes. All right, what? Any questions on that before we come on? It's starting to feel easier. Feels like we've been doing this for like 4 weeks almost. Starting to feel easier. Do we want to do another arc length or another surface area? Did we do?
Arc length, maybe.
We did one arc length. Let's check the second arc length one out. Well, it looks like it's going to be a perfect square trinomial one. I can't believe I didn't give you a sample one that wasn't a perfect. I guess this perfect square trinomial one's the hardest, so I chose 2 harder ones just to make sure. If you can do the harder ones, you can do the easier ones. Okay, so there is our curve. So this is a curve. You would not ever want to try to graph that. Right, that you do not need to know the graph of. But you know it's a function, right? That's a function. You're plugging in an x and you're getting out a unique y. There's no plus or minus thing. There's no square root. There's no division by 0. So we don't have to, it is a function on this interval. So all we have to do is visualize a wiggle in quadrant 1. That doesn't really matter. And we want to find the arc length of it. So we know that we are going to have to find its derivative. Because the generic formula for arc length, remember, is the integral of the square root of 1 plus y prime squared. Right, that is our generic formula. So we need the derivative of the function. So y prime, on the test, one of the most common mistakes that I see is getting the wrong derivative. And then everything that follows is, a mess. So if I were you, I would go into my math lab, go to the study plan, and even if you just practice some of the derivatives of functions that they give you for arc length, just as practice, or the ones for surface area, just to make sure you're getting your derivative right. You don't want to blow the derivative part. So it's not a polynomial, but we differentiate it as if it is. I would use the power rule. So 4/3 comes down. 4/3 times 3/4 is 1. Those are reciprocals of each other. And then we subtract 1 from the exponent. So 4/3 times 3/4 is 1. We subtract 3 over 3, and we get x to the 1/3. Second term. The 2/3 comes down. And when the 2/3 comes down, we have a 3 in the top and the bottom, so the 3's cancel. 2 over 8 is 1/4. And when we subtract 1, we get negative 1/3, and then the derivative of 6 is 0. So there's the y prime. And we know that with arc length, we need to get y prime squared. And so here's the part that you want to be patient. You think of this piece right there as A. You think of this piece, not including the minus. B is to the right of the minus. That's B. So we're going to do y prime squared So we're going to take x to the 1/3. We're not going to square it out. We're just going to leave it like that. So that's a squared. And then minus 2 times a times b. And remember, b does not include the minus sign. So there's minus 2ab. And then b, which does not include the minus sign, is squared. So there's perfect square trinomial. And our focus is on that middle term. If that middle term turns into -1/2, then it's a perfect square trinomial problem, one of the sneaky perfect squares. So we're just going to copy the first part and the last part down. Let's focus on the middle. And we get -1/2. -2/1/4 is -1/2. Everyone agree that x to the 1/3 and x to the -1/3 multiply to 0? Excuse me, multiply to 1, the exponent is 0. X to the 1/3 times x to the -1/3 is x to the 0, which is 1. All right, so this is one of those sneaky perfect square trinomial ones. So now we're going to add 1 to both sides. And when we add 1, the only thing that changes is that middle term goes from -1/2 to +1/2. So we know that it's still a perfect square trinomial, and it factors into almost that. So it's going to be that plus 1/4 x to the -1/3 quantity squared. A squared will be there, b squared will be there, and then the middle, you're going to end up with a +1/2 if you do the plus 2ab. That allows us then to say that s is the integral. The limits of integration, they told us 1 to 27 with respect to x. Square root of all of that. And then the square root and the square mash each other up. They annihilate each other. That's got a square on it.
So what happened to the 1/2 there?
So this is a trinomial that's a perfect square trinomial, and it factors into a plus b squared.
Okay.
So the same way, there's no, right here, if you square this, you end up with -1/2, so we're just going backwards. We're factoring it. So this trinomial here factors into that. So the +1/2 comes about by doing 2 times a times b. And if you were to square this out, the middle term would be that times 2. And that times that, the x to the 1/3, the x to the -1/3 is 1. And 1/4 times 2 gives you that. So it's a perfect square trinomial. And then here, the square root and the square undo each other. So we're left with an integrand that's pretty easy to integrate. We can just use the power rule. We have that. And the power rule, we add 1 to the exponent divided by the new exponent. So add 1, we get 4/3. Divide by 4/3 means multiply by 3/4. And then over here, we add 1 to the exponent. So we add 3/3, we get x to the 2/3. Dividing by 2/3 is the same as multiplying by 3/2. I got lost there. So we added 1 to this, we get 2/3. So we add 3/3, we get 2/3. Divide by 2/3 means multiply by 3/2, so we get 3/8. And then this goes 1 to 27. All right, so that gets us through the bulk of it. Is there any question on any of the steps there? Plug in the 27. 27 is a perfect cube, so the cubed root of 27 is 3. 3 to the 4th is 81. Same idea for the second term here. Cubed root of 27, that's 3. 3 squared is 9. And then we subtract off what we get when we plug in the 1. So we're going to get that. And then whatever that simplifies to. I can type it in and do it in a second. Any mysteries? So when we look at these, we actually got through a fair number of them today. Any of them that are causing you let me just point out one other thing about the review again. At the very bottom, don't forget about the integrals of the semicircles. Just review that to make sure you've got your semicircles down. And I wanted to ask you a question and make sure that it was clear to you. Let's look at this one. So this is a circle of radius 4. The equation for the lower semicircle, we have the negative there. But then over here, for area, I do not have the negative there. Can anyone tell me why there is no negative in front of that square root?
You can't have negative area.
You definitely can't have negative area, but what's the mathematical reason there's no negative there? That's a conceptual idea that area can't be negative. Do you agree that this is a vertical rectangle? How tall is that vertical rectangle? It's a vertical distance, so you would do the upper y minus the lower y.
0 minus the equation.
The upper y is 0, so the height of this rectangle right here is 0 minus square root 16 minus x squared. So the curve down here is this negative square root. The curve up top is 0, so it's 0 minus square root, which is what makes it positive. Right? If you're trying to find the area here, it's the area between two curves. It's the area between that lower semicircle and the upper curve of y equals 0. And that's very similar to this one. The left curve is negative root. And if we want to find the area of this circle, we're doing this horizontal distance right here, which is going to be right minus left, which is why that then becomes positive, because the right curve is x equals 0. The left curve is x equals that. So 0 minus a minus makes it positive. Okay, so let's stop there. Questions between now and Thursday? I'm in the Math Center tomorrow. You can email me. Use the Ask My Instructor if it's a My Math Lab question. Or just email me and say help. Or post something in one
Maybe just a picture of someone drowning.
picture of yourself drowning.
Yeah.
Use AI. Look at me, I'm drowning.
Yeah, I mean,
Somebody's
hopefully I'm not that far.
burying me in math symbols. Good luck studying.
Good luck, right?
That would be so.
That cuts into my homework I was going to do during lunch.
Have you ever done something?
I've only done homework for this class.
Yeah, I know. I
You know, you
glad
know,
to do this.
so funny. So what's
That keeps happening in chemistry. Our teacher doesn't know.
No way.
So I just have to log on to Alice and push it to the other students. It's not predictable either.
All right, good luck studying.
Sometimes
See you on Thursday.
Oh, helpful. Yeah.
Yes.
have to get lucky. Yeah. Right. Well, good luck.
Thanks, you too.
We'll see you all Thursday.
Yep. All right, take care.
It's done the testing.
I'm concerned about the rest of this class.
They can scan through, I would just make that.
If you looked at the practice exams for the other
I'll be grading, I'll
chapters,
finish the grading on
Nope,
Monday.
not gonna go there. Don't do that to
I'll
yourself.
keep it to myself then.
Why would you have done that?
Will that work? Okay. I'll do that.
I can't
Yep.
speak anymore, or I'll spoil the surprise.
Well, I'm here now.
Yes, please do that. Please do that. And then also, so when you're doing your worksheet, so do it in here.
Okay.
Do it in that one, because that's when I go to the class notebook to grade them, I'll pick that one, that's where I'll see all the work, so.
Okay.
Yeah, so then it'll
I got a lot.
jump out at me.
Oh, it's only.
All right, glad you're back.
Oh, God.
See you on Thursday. Oh, well, I won't see you on Thursday. See you in the future.
Yeah.
In the future.